All right, welcome ladies and gentlemen. This is the first Redox video, so you're going to need your note packet just right open to page 1. That's all we need. You might also need your reference table, the periodic table at some point. In this, I'm going to be introducing you to what Redox means, what it is, some definitions, and a review of oxidation numbers, which we have seen before. So first up, what happened in the green chunks and foil lab? Well, obviously, because this is our redox unit, this is what is called a redox reaction. And in this particular reaction, the aluminum was what was called oxidized and the copper was what was called reduced. What does that mean? Change of charge. Both of these species, the aluminum and the copper, underwent a change of charge in different ways, and that's what makes it a redox reaction. And because of that change in charge, we got all the observations that you saw. So break it down. So the aluminum was oxidized. What does that mean? Well, oxidation, by definition, is the loss of electrons, E negative. Now, when something loses its valence electrons, which the aluminum did, the charge will change, because electrons are negatively charged. So if you switch how many electrons you have, your charge is going to change. So what does that mean that the aluminum was oxidized? Well, we started with the aluminum foil. So that was the foil, and that's the aluminum foil right there in this little, what's called a half reaction. And the aluminum started with all of its electrons. So it started with all 13 of its electrons. It was intact. And then when it reacted, the aluminum lost just its valence electrons. So we have this process right here. The Al foil, the solid, became Al plus 3. Now notice this is aqueous. So the aluminum, when it lost its electrons, it actually dissolved into the water and it became a colorless solution. And also these 3 electrons down here, electrons are being produced / lost. The aluminum started with these 3 electrons attached to its atom, and now these 3 electrons have separated from the aluminum, i.e., they were lost. So oxidation is the loss of electrons. Now, the copper, on the other hand, underwent reduction. Reduction is the opposite of loss of electrons. Reduction is the gain of electrons. And I know you're probably thinking, well, why do we call it reduction if you're gaining something? And we're going to talk about that in this unit, don't worry. But the gain of electrons. Again, electrons are negative, so charge changed. Again, in redox reactions, you have change of charge. So the copper started with the +2 charge when it was in the copper 2 chloride solution. So this is how we started, right? And notice we have this +2 charge. And this stuff here, the aqueous stuff, that's the blue that you saw in solution. It was due to that copper +2. But when the copper reacted with the aluminum, these electrons right here that actually came from the aluminum got added onto the copper +2 ion, and the copper gained 2 electrons, and it turned it into copper solid. Now, copper solid, this is that red-brown, aka the copper color, stuff that you saw in the beaker. And notice when we look at this that the electrons are actually reacting. Right? They're not products anymore like they were in the previous one where the aluminum started with all of its electrons and then it sort of let 3 of them go. Now the electrons are actually reactants. Hey, reactants. Hey, reduction. Hey, aluminum electrons are reactants in reduction. And this shows the fact that the copper is gaining. The copper didn't start with these 2 electrons. Those 2 electrons were added on to the copper, and the copper ends, this is a massive point, the copper ends with more electrons than it started with. And looking at these 2 processes individually, you have your aluminum. This is called oxidation, what the aluminum did, and the copper, this is called reduction, and we see that the charge is changing. The aluminum started at a 0 charge because there was no charge written, and it ended at a +3 charge. And the copper started at a +2 charge, and it ended at a 0 charge. The oxidation number changed, the charge changed. This is what is called a redox reaction. The overall process of both of these things happening at the same time is where we get this word redox. It comes from the first bit of reduction, and it comes from the first bit of oxidation. It's called a portmanteau. It's a combination word of two other words. So redox, it's reduction plus oxidation. Because both of these things happened at the same time, because we had the oxidation plus reduction occurring in the same beaker, we call that a redox reaction. One thing was oxidized, one thing was reduced. And a massive point with redox, one cannot occur without the other. You have to have both processes occurring at the same time, and that's what we call redox reactions. Redox reactions, reduction plus oxidation. One thing loses electrons, something else gains electrons. Now, if we look at the two individual processes, we have, again, the aluminum starting at 0 and winding up at +3. This is a loss of electrons, aka oxidation. We have the copper starting at +2, gaining 2 electrons, ending at 0. This is gain. Notice the aluminum is losing 3 electrons, and the copper is only gaining 2. But this right here is actually the overall reaction. And notice that the coefficients in this reaction are not the same as the coefficients that are up here. And the reason is due to this. The law of conservation of charge. The law of conservation of charge states that the charge on one side of an overall balanced equation, or even a half reaction, must be equal to the charge on the other side, i.e., the number of electrons that you lose must be equal to the number of electrons that you gain. And we don't have that here because we have 3 and we have 2. So the overall reaction, again here, is not simply a combination of the two individual processes, but instead what we had to do is actually multiply the aluminum process by 2 and the copper process by 3. Because when we do that, I'd get 6 electrons for the copper, and I would get 6 electrons for the aluminum, which allows us to obey the law of conservation of charge. So this idea that charge must be the same on both sides of the equation is a really, really big one in redox, and that's going to govern a lot of ideas. So a little way to remember what's what. How to remember these definitions, because these are really important definitions. And we do have a little mnemonic device called Leo the Lion Says Grr. Leo the Lion Says Grr. That's going to help you remember these definitions. Loss of electrons, LEO, is oxidation. Gain of electrons, GER, is reduction. So Leo the Lion says grr, and I'm not going to take credit for that, but I do have a little Leo that I'm going to show you in class, as stuffed animal. Now, to be very, very clear, half reactions. Half reactions are not overall balanced equations. There are processes that show just oxidation or just reduction, so they don't show both of them together. So they're not a full equation. They are literally half of a redox reaction. So this right here is an example of a half reaction because it's only showing a single process. So in this process, we are showing the sodium going from a charge of 0, because there's no charge, to a charge of +1, and we're showing this electron separating from the Na, i.e., it's being lost. Right? That electron is no longer part of that original sodium atom, so that electron is being lost. So that is called oxidation. So this is an oxidation half reaction. Now, in an oxidation half reaction, because you are losing electrons, your electrons will always be products. They're always going to be separated from the original thing. And because you're losing a negative charge, again, electrons are negative. That's a huge thing to remember in this unit. If you're confused in this unit, it's probably because you're having trouble with remembering that, because that's a really core idea here. If you lose a negative charge, your atom or your ion will become more positive. So in oxidation, you become more positive. Because, little thing I said, you know, if you have a negative person in your life or a negative influence in your life, if you cut them out of your life, if they're no longer a part of your life becomes more positive, right? Everything gets happier, everything gets better. So it's the same thing with oxidation. If you lose a negative, you become more positive. Now, this down here, the sulfur, is also an example of a half reaction, but now this is a reduction half reaction. So notice that the sulfur is having 2 electrons added on, instead of having electrons be separated from. So this is showing a gain of electrons, which is the definition of reduction. So we're adding electrons onto the sulfur is gaining electrons, and this is reduction. Every time we have a reduction process, a reduction half reactants, your electrons are actually going to be reactants to show that they're adding on to something, that they're combining. It's kind of like a synthesis reaction, right? Your electrons are combining with something to make something else. And our charge, our atom, our ion becomes more negative. So in reduction, we become more negative because we are tacking on additional electrons. So we have a couple different half reactions here. We have potassium, oxygen, and chlorine. And in this half reaction, K goes to K plus 1 electron. Notice that our electrons are on the product side. That indicates a loss of electrons. These electrons are separating from the potassium. Notice also that the charge on the potassium, it goes from 0 to plus 1. Charge increases, right? Charge increases. Right, it becomes more positive. So that means it lost electrons. In oxidation, you become more positive. Versus this one right here. Now notice that we have the electrons on the reactant side, and that our charge, our oxygen went from a 0 charge, because there's no charge written, to now we have a -2 charge. So now we have a gain of electrons. We notice that our charge, that we're become more negative. So that indicates reduction. Charge goes down. And then the last one, notice again, we have the 2 electrons on the reactant side. We are adding electrons on. Charge decreases. We're becoming more negative. Hence, reduction. Now, a huge part of redox reactions is the ability to determine oxidation numbers. We have done this before, but now is a critical time that we review this. So what are oxidation numbers again? They are positive or negative charges that determine the extent to which something has had electrons added on or had electrons removed from it. So you can kind of think of it like a pseudo charge. Sometimes it's the actual charge of the species, sometimes it isn't, but you can think about it like how many electrons have been lost or gained in this thing. It's kind of like a charge. And almost all redox processes start by comparing oxidation numbers. If you look at the difference in oxidation numbers in a redox process, you can figure out what was oxidized, what was reduced, which is a really key thing for us. So just a review of our rules for assigning oxidation numbers. You've seen this before, but it's been a while. So anytime an element is by itself, its oxidation number is 0. So for example, in these things that we've seen, if you just have like sodium by itself and it's not bonded to anything, there's no charge written, its oxidation number is 0. Oxidation number of a monatomic ion is equal to the charge of the ion. So what do I mean by that? Well, if we had the manganese ion and it was at a +7 charge, then the oxidation number for the manganese would be +7. The charge that's here, right, that's just the oxidation number. Group 1 ions are always +1 when they're in a compound or when they're aqueous. When they have a charge written, they're always +1. So lithium, sodium, potassium, rubidium, cesium, they're always going to be +1. Group 2 ions are always +2. Beryllium, magnesium, calcium, strontium, barium, right? They're always going to be +2. So we know that. We know that for sure. Hydrogen is almost always +1 when it's in a compound. When it's by itself, it's going to be 0, but if it's in a compound, it's usually going to be +1. We do have one exception, and that's when their hydrogen is bonded to just a metal, so it would be just a metal plus a hydrogen. So for an example here, that would be NaH, sodium hydride. Because the sodium is +1, the hydrogen would have to be -1, because you might also remember we have a rule that says the oxidation numbers have to add to 0. But that's, again, it's just a metal plus hydrogen. That's the only time where hydrogen is going to be -1. And then the final set, oxygen in a compound is usually -2. If you see oxygen, you can kind of go ahead and assign a -2 charge, except in the case of hydrogen peroxide, in which case it is -1. But that is the one exception that we need to know for oxygen. Most of the time, it's going to be -2. Halogens. So fluorine, chlorine, bromine, and iodine, right? Group 17. They're -1 when they're in a binary compound. Binary compound, though, means only 2 elements. So, for example, HCl, right? Hydrochloric acid. The hydrogen is +1, the chlorine would be -1. That's a binary compound. But if it's not a binary compound, then this rule isn't true because, for example, in KClO4, the chlorine is going to have actually a +7 oxidation number. So it's totally different if it's in a ternary compound. So halogens are -1 when they're in a binary, but they can absolutely change to be something different if they're not in a binary compound. And then the last rule is a really big one because it kind of covers everything else on the periodic table, all the other elements we haven't talked about. Some of the oxidation numbers in a neutral compound is 0, meaning you add everything up, you get 0. Or the sum of oxidation numbers in a polyatomic ion is equal to the charge on the ion. So we can figure out what other things are based on this final rule that says they've got to add to 0 or they have to add to the overall charge. So we're just going to end this video with a little bit of practice in this. What are the oxidation numbers for each atom in the following compounds? And we have 3 of them. In this first one, we have an element that is alone. Notice that this hydrogen is not in a compound, so we're not going to give it the +1 charge. Hydrogen is +1 when it's in a compound. It's not in a compound now. So now we're going to that first rule. An element that's alone when it's by itself is 0. So I would say that the hydrogen here has a 0 charge. Its oxidation number is 0. In the next one, I have S2O32-. Which of these do I have a rule for? Well, I have a rule for oxygen. I know that oxygen is usually -2, but I don't have a rule for sulfur. So I'm going to use that final rule to figure out the charge on the sulfur. So again, this is this thing where we want to go, there are 2 sulfurs. Right, I know that because of the subscript. 2 sulfurs plus 3 oxygens has to equal the overall charge on the species. So 2 sulfurs plus 3 oxygens has to equal -2. And I know that oxygen is -2, so I can plug that in there and then simply solve. So 2 sulfurs plus a 3 times a -2 for each oxygen is equal to -2. The rest is just solving. Add 6 to both sides. I have that 2 sulfurs is going to equal +4, but that's 2 sulfurs, and I want each sulfur individually, so I have to divide by 2. So I get that sulfur is +2. So when I'm reporting this compound, I'm just going to write it over here and then erase it. I would say that sulfur is +2 and oxygen is -2. So those are the oxidation numbers in this polyatomic ion. So I had to work out what the sulfur was based on the fact that I knew that oxygen was -2 and I knew that the charge would add to the overall charge in the ion. And in the last one, I have potassium dichromate, K2Cr2O7. I need to figure out the oxidation number on each element. What elements do I have rules for? I have rules for potassium because potassium is in group 1, so potassium must be +1. I have a rule for oxygen. Oxygen is -2 almost all the time, but I don't know what the chromium is, so I have to figure it out. I don't have a rule for chromium. So again, I'm going to set up something like the previous one. 2 potassiums, the 2 is coming from the subscript on the K, plus 2 chromiums, again, subscript, plus 7 oxygens, and I like to write my oxygen as OX, so it's different from 0, is equal to the charge in the compound. Well, what's the charge on the compound? Charge in the compound, nothing is written there, so the charge on the compound is 0. Has to add to 0, and then it's just plugging in. 2 times +1 plus the 2 chromiums plus the 7 times -2 for the oxygens is equal to 0. Right, this is 2. This is -14, is equal to 0. I'm just going to combine the 2 and the -14, combine like terms. 2 chromiums plus a -12 is equal to 0. Add 12 to both sides, and I get 2 chromiums is equal to +12, but I have to divide by 2 because I just want 1 chromium, right? And so I get that chromium, let's see, I'm going to put it up here. Chromium must be +6. But again, I wanted you to tell me what each oxidation number was. So then you're also going to tell me that potassium is +1 and oxygen is -2. So we're going to be practicing reviewing oxidation numbers and some basics of redox, those definitions of redox.